All right, it's 2 o'clock Eastern time, so we'll go ahead and get started. A few notes before we jump in. Just a reminder for everyone to keep their microphone muted during the presentation so we don't get too much background noise. And also, if you have questions, feel free to type them in the chat or interrupt during the talk. Our speaker is willing to take questions during the talk as well. And we'll also have time at the end for questions. So there are a couple of different ways to ask questions throughout. And with that, we're happy to introduce Dr. Göbel, who's a postdoctoral research associate at Goethe University in Frankfurt. And we're going to hear today about Coulomb dissociation of oxygen-16 into carbon-12. Take it away.
Thank you. Yeah, so the Coulomb dissociation, you will have an evening now. Well, half of the people there, which are not far away from me, will have an evening, and you will have a hopefully nice afternoon with me in the lab. And so when I talk about Coulomb dissociation of oxygen-16 into carbon-12 and helium-4, this is basically what I think of. So this is a quick view at what we've been doing for more than 2 years until we were able to do a first experiment in April 2019. And so we, from the first sketches of how we might build the detectors that we needed to drawing things with a computer-aided design to working with the workshops that we have, building everything and then setting everything up that we need at our lab at GSI here in Darmstadt. And well, yeah, we're driven by this idea that we have the carbon and oxygen here, and they are so important for us. And the moment, or the time period in a life of a massive star where this is produced, and where the ratio of carbon and oxygen is determined, is well, during the helium burning phase that stars do, where you make carbon out of 3 helium nuclei, and then, well, you have carbon, you have helium, and the next step that follows from that is that you make oxygen out of them. And these reactions are together, so this helium burning, which makes carbon, and then the carbon plus helium, which makes oxygen, it determines what we have, what is the ratio of that. And so this is the reaction that we are interested in. A star, well, that has been doing it, will be doing it somehow. We're in this period of its life is Betelgeuse. And I guess you've all read the news that were there at the beginning of the year when newspaper articles said, waiting for Betelgeuse to explode. Or Star Watch, Betelgeuse, a fading star heading for an explosive end. Well, and a giant star is acting strange and astronomers are buzzing. So what is that? What was going on? Just to remind you. Well, Betelgeuse is a red giant star, and it's part of the constellation of Orion, which is a constellation that you see in the night sky in winter. So currently, it's not a good idea to look for it because you will not see it in the northern hemisphere, at least. Betelgeuse is the upper top one. As it's the shoulder of Orion, and then you have kind of the counterpart, which is also a large but bluish giant star, which is Rigel. And so there is Betelgeuse, and what we saw was that the normalized flux, or that we got from Betelgeuse, was decreasing. So over months, from the normal flux that Betelgeuse being one of the brightest stars in the night sky, it went down to about 1/3 of the flux. So at some point in February, as you see here, Betelgeuse was at 35% of its usual brightness. And of course, there were some hopes that this might be a sign that it will soon go a supernova, which would be a beautiful event, of course, for all of us to see in our lifetime, and to be able to watch an object in the sky that becomes as bright as the full moon. So what is just some facts about Betelgeuse? So it's about roughly 650 light years away. It has something like 20 solar masses and is as large as 1,000 solar radii. So if you put it into our solar system in the center, that's, if you have a look at the picture on the right, it reaches up to the Jupiter orbit. So it's really a large giant star. It's a bit colder, so that's why we see it as a red star in the night sky. And it's relatively young because it has started as a very massive star. It is still a massive star. It's only about 8 million years old. And we do know that it's a semi-regular variable star. So there is some variation in its brightness that we know. Still, that was kind of surprising that it went that dark. This is some data over the last roughly 50 years, how the brightness of Betelgeuse varied. So you can see exactly that. It's a variable star, and you see these pretty big variations. But looking at the very right of this plot, you see that it drops. So the brightness of Betelgeuse had dropped, well, to about a third of its usual or normal brightness that it has. Well, however, it did not explode. Otherwise, you've read some news until now. You have not. Pictures that have been taken, as you can see here, is roughly a year apart. So January 2019 on the left, an actual picture of Betelgeuse. So that star is so large, you can make a picture of it. It's not only a small dot on the night sky. And then again, looking at it in December 2019, well, obviously it was not as bright as on the left side. And the current statement is that there's probably some dusty thing that was around it which made it look very dark for us. And now, well, current picture, or let's say a few weeks ago, the brightness is back at its normal value. So unfortunately now, or currently, Betelgeuse is probably not about to go supernova, but it will somehow, sometime between now and 100,000 years. So there's still some hope we might actually see it. So, but this star, so it has been a lot of news about it. We have been hoping for something to happen, but we thing that we know is, well, it's somehow a star that is in this life circle, its life somewhere at this point, having done this helium burning, having done carbon and helium fusion to make oxygen, and there might be phases where it will do it again very soon. And summarizing life stars, this is a very general overview what happens in the life of a star. So let's just have a quick look at that. So in the center, you have some nebula where you can make stars out of gas and dust. And then you can basically separate it into two life paths that stars may have. So if you have the light stars, so they're not very heavy, they maybe have a mass similar to the sun or not much more, then they will go the left path. So they will spend billions of years making helium out of hydrogen. So this proton-proton chain that we have making helium in the first step is what they do for billions of years. Then they eventually become a red giant. And at the end of that part of life, they will throw away the outer shells, which makes a nice planetary nebula on the sky with beautiful objects to look at. And the rest will remain as a white dwarf and cool over time. While if the star is rather massive, so say it's about 8 to 10 times more massive than our sun, it will go the right path. So it will grow to a red supergiant, and that only takes millions of years. So the life is very short of such a massive star. And then at some point it will go supernova. And the rest, as a result of that huge explosion, you either have a neutron star as a remaining object, or you have a black hole. So this is the rough picture of what happens to stars, depending on the mass they have. The thing that is not so clear up to now is well, what is the mass that it becomes a neutron star, and what is the mass that it becomes a black hole? So we're talking roughly about a range of masses, something like 16 to 50 or 60 solar masses. Somewhere in between, there is this border or this limit where it will go, where it be so massive that it will become a black hole in the end. While computer simulations, stellar models, and combining that with nuclear physics data that we have kind of put a bit limits on that. One of the things that is, it's still not defined, or has too large uncertainties to really put something on it, put a tag on it, is the nuclear physics. So, and the nuclear physics of how much carbon and oxygen is there when it goes on the path towards the supernova. And as I mentioned, one of the important reaction for that is the fusion of carbon and helium to oxygen. So while we're looking at something at atomic nuclei in the lab, trying to understand what their cross-section is for the fusion, what the rate is in the end for this reaction, they define what happens to a star. So what the star's fate in the end then is. So if we have to find out what is the cross-section of this reaction with low uncertainty, so that we can actually pin that down, and then we can take care about all the other uncertainties that these models have. Okay, so I've mentioned these two reactions. So the upper one is this triple alpha process, or helium burning, which is an equivalent name. You make carbon out of 3 helium nuclei. And the lower one is then the step that happens right away, because you have carbon, you have helium, and that fuses to oxygen then. And so somewhat after this has happened in the core, you have a star that, just to have a model or picture, you have a star that has a carbon and oxygen core, you have a layer of helium, and you have an outer huge envelope of hydrogen. And also in these envelopes, then several episodes of helium burning and take place in outer shells then again. So these reactions are the important ones, having produced something like a star that looks like that. So we need to know more about this information. And this is a bit summary of the data that we have so far for this reaction. So this is the reaction carbon 12 plus helium goes to oxygen 16. And shown here is as a function of the center of mass energy that the carbon and the helium have when they fuse, is the S factor. And the S factor is, let's say, basically the cross-section, but well, all the nuclear physics part there is, kind of separate from that. So you have, imagine you have, of course, the cross-section as a function of energy. And if there are no resonances, for example, then the S factor is smooth and does not change with energy much. So that is why this S factor is something that we really actually like to use looking at that. Okay, first look at the pictures. That is nothing that does not change much with energy. It does change with energy because there are resonances. And on the upper part in this picture, you see the E1 component, and lower part, the E2 component, which are both relevant for this cross-section and depend which levels you have, and if you need an E1 transition or an E2 transition to move from a level to another one. Okay, and as you see, the data points that we have from experiments that have been made over the last decades, and then a fit to data on our matrix fit in the red curve. The important thing to note is that dashed line that is on the left, where in the upper part you have this written 300 keV. So that's where we want to go. 300 keV is the energy where that reaction matters most in the star. And you see that the data points are kind of a bit far away still from that. And also the lower the energy with these data points, so if you look at the center of mass energy for 1 MeV, and you look in the lower part where there's the E2 component, you see that the uncertainties of the data points are really large. Okay, so this is not as satisfactory as we actually wish to have it. The good thing is about the approach that we have with this Coulomb dissociation measurement, which I'll explain more in a few moments, is that it detects, or it will bring us data for the E2 component especially. So this is why there's this area marked in grayish, in a grayish color. This is where our method will contribute to the data that we need. And we hope to really, for one thing, reduce the uncertainties that we have at the lower energy range. And the other part that we will do, we just get data over large energy range. So we hope to really contribute largely to the E2 component. Okay, so with that, I will take you to our lab, what we actually do. And in our lab, well, you can usually find us like that when setting up the experiment. This is at the lab at R3B at GSI. Well, GSI Fair, if you don't know it, is located in Darmstadt, which is about 30 kilometers south of Frankfurt. And there you have the facility, which is GSI, which was established now, well, about 50 years ago. So it just had a big birthday. And it's the upper left part that you see in the picture where you see buildings that look like office buildings and these large halls. So this is what we have right now. And the huge complex with the new ring facility, ring accelerator facility that we will get within the next years is FAIR. And the experiment R3B has, well, has developed from being land at GSI, has developed already to being R3B, and R3B will then move to FAIR when FAIR, the accelerator complex, is ready. Currently, so this is a picture of how it currently looks like. So you see the GSI complex, which is already very large. And on the right, you see the huge construction site of FAIR, where they are now building the tunnel for the ring and moving forward actually quite quickly. R3B, this experiment where we're working at, is located in this target hall on the right end of the GSI area that we have currently. And this is how it looks like if you enter our experimental hall. This is how it looked like for our experiment in April 2019. So right before we closed everything to have Beam in the cave, I went in to take a video of that, how it looks like. In this video, it's such that now the beam comes from the right. So pointing at that, the beam comes through these quadruple magnets, this yellowish thing in the wall, and comes in. So I'm passing now under the beam line and moving to the back of our experiment, passing the large magnet that we have, this huge metal thing, passing a huge vacuum chamber, which is, you see a bit here on the left. And then, depending on the experiment that we have, there's this large tube where fragments may travel under vacuum and be detected in the back by different detectors. So different setups, different detectors, what the experiment needs. Now looking back at the large vacuum chamber that we had to use and where we had to put our detectors in for our experiment. Okay, so what do we actually want to do? So I don't know how familiar you are with this Coulomb dissociation idea. So here's what is behind. Well, we are interested in the reaction carbon-12 plus helium-4 goes to oxygen-16, and you have a gamma in the outgoing channel. this is what we want to know. We want to know what the cross-section of this reaction is. Perfectly, it would be perfect if we knew it in the very low energy range where it's relevant for the stars. But this is hard to measure. So there have been over decades many attempts to do that in underground labs and so on. And this is not what we're going to do. So we're trying to do the inverse reaction, have a look at that. So we break up oxygen-16 by exciting it and into helium-4 and carbon-12. But we do not have a photon source for that, in a sense that some laser facility or whatever you can imagine shooting photons on oxygen-16. That's not what we do. Coulomb dissociation has this idea. You shoot in an oxygen beam and you shoot it onto a lead target, which is here very schematically a lead atomic nuclei. And as the charge of this nuclei is so high, so you have a charge number of 82, you have a very high electromagnetic field around it, so a Coulomb field. And this Coulomb field will then excite the oxygen nuclei such that it may break up into helium and carbon. And this is what we use, and that's where the name Coulomb dissociation comes from. So we excite the nuclei in the Coulomb field and eventually it breaks up. So we have to look at that. And here's a theoretical calculation of the Coulomb dissociation cross-section. This time we have a cross-section here, which is provided by our colleague Stefan Tüppel from Darmstadt. So this is what we have. Again, now looking in red, you see the E1 component. In, well, something purple, you see the E2, and the sum of it then in black. So this is what we'll expect to have for a Coulomb dissociation experiment. And if you now look at that, and you see that on the axis there is Mach millibarn per MeV, and you look at the y-axis where you see that, for example, at 1 MeV energy, we're somewhat at 10 to the minus 4 millibarn per MeV, that this is going to be tough. So this cross-section, so the actual cross-section, the carbon plus helium goes to oxygen is very low, and also the Coulomb dissociation cross-section of the inverse reaction is very low. And this is what we have to attack, kind of. This is a huge problem this reaction has. The cross-section we know is so low that it's hard to measure it. And so, but okay, we're trying to attack it in that way. For our experiment then, if the cross-section is so low, our idea is to have a high intensity beam. And so we're shooting in oxygen on the lead target. And we need about 1 or 2 times 10 to the 9 ions per second. So 1 billion ions per second coming in from the accelerator. And this is nothing that typical detectors that we have can handle. So say we have scintillation detectors in our experiment. If you shoot 1 billion ions per second on it, you will just see light. You will not see anything else anymore. So this is not what we can do. We cannot shoot this beam on our detectors. So the setup we chose is that we put our detectors such that there's a slit in between, and we just let the billions of ions per second pass. And if there's a reaction, well, depending on the geometrical acceptance, of course, but a part of carbon and helium that may result as fragments, as we call them, from the reaction, they hit the detectors. And this is what we can detect. And as well as the cross-section is so low, there are, of course, additional other nuclear components that also happen, nuclear reactions that happen in the lead target. But still, the estimate was that this is fine. So our detectors can handle that if we set it up like this. And to make sure in the experiment that we can handle it and set up the experiment as we need it, we put all our detectors on such slides, and we were actually able to adjust the slits in between while we're setting up, because we were not so sure what is the beam quality, what will be the diameter of the beam. I mean, focused as much as we can, but we were not sure what happened, so we were flexible and adjusted everything during the setup phase for the experiment. And then this is a view at our setup, a schematic view that we had. So we're looking for this reaction. And this is a view, of the setup, and you're looking from the top. So if, in the video, I was just coming in, passing on the beamline and passing the magnet going to the back. This is a view from the top. So you have the ion beam, which is marked there in green, coming from the left, and we have some active collimators, Rolus, which is, rechts oben, links unten, German thing. And then the beam hits our target. Behind that, we had fiber detectors. And then we were shooting our beam, and as well the fragments that come from a reaction through a magnetic field. When they're charged, as they are, so the carbon and the helium we're looking for, as well as the oxygen beam are charged, they will be deflected in the magnetic field. And after that, we have more detectors to track where these particles actually pass, marked here as fiber detectors. And then a time of flight wall, TOF D, which in the end would detect the charge of the particle that hit this detector. And you see everything, so besides the target, has slits. So this is the idea of the setup. We will not stand in the way of this high intensity beam, we'll just let it pass. And the first detector then to actually measure the intensity of the beam was then a C-tram, which I'll show you also in a second. Yeah, and then it passed. So that is our basic setup. And one more thing that we had put around the target is Khalifa, which is a gamma detector. So if you have excited fragments in the outgoing shell, so you might have an excited carbon fragment, then you can detect the gamma that is emitted there. Okay, a bit more into the lab. How did that actually look like? So this is the active collimator that we have used. This is Rolu, and it basically consists of 4 of these rectangular scintillator plates, which are here wrapped in aluminium. And then they are mounted such that you have this rectangular shape where the beam may pass. So you have these slits in between. And you can adjust the slit that it has. Let me show you. So we had in our lab, when we're setting up, this is mounted in a vacuum chamber, of course. And then, well, we can adjust the slit as we want it then for experiment. And you see, these are 4 plates that then in the end you have kind of a rectangular shape where the beam can pass. Okay, so we have the collimators. Then around the target, and the target is mounted in this ball, in this metal ball. And around that, we had the gamma detector prototypes of that, of Khalifa. Then we have a target wheel inside. So looking inside the chamber when it was still open. And it's a target wheel where we can choose a lead target if we had different lead targets, and we had other targets and empty targets for our experiment. And so while you're running the experiment, you change the targets in between. Then we had the first fiber detectors, and they were mounted between the target and the magnet. So if you have a look at the picture, on the right, you still see these barrel-like things, these metal boxes where the Khalifa gamma detectors are in. And on the left, this huge tank, this metal tank that we have is where our magnet is inside. And this chamber, where you see the electronic cards on the side, was a vacuum chamber we designed and put there to house fiber detectors. And this is how they looked like. So on the right, you see the pure fiber detector that we had. This is the active area of the fibers is roughly 10 times 10 centimeters to give you an idea about the size. And we put there scintillation fibers. So, and they were really small. So we used fibers that had that were rectangular shaped, and they were the side of it was 200 micrometer thick. So really, really, really thin fibers, one next to the other, so covering the full area. And so, well, you now need to calculate if it's roughly 10 centimeters and 200 micrometers of scintillation fibers, then it's about 500 that we have here next to each other. Then at the end, they are read out. So we put them on photomultipliers to read out the light that they give us. On the left, you see the picture when it's then wrapped with a black foil to shed light. So we only want the light from the particles that is generated inside the scintillator itself, and that's some light that might come from outside. So we put a foil on that and we mounted it in this setup. And also here you can already see this idea that we put it such that we can move it later. So it's on, the detectors are both mounted on drives, you see in the lower part of the picture, and then all the scintillators, the scintillators that are read out by photomultipliers on top and on the bottom, and then going to the readout to the outside of the vacuum chamber. And that we put in the chamber, and then it looked like that. Where you have an idea, so the part that is covered with this black foil is where the scintillation fibers are, where the active area of the detectors is. And then you have the slit in between that we then adjusted during the experiment. So that is the front part before we go into this large magnet glass that we have. And so let's look a bit at what was behind that. So again, if you looked at this picture, there were fiber detectors again. So we again want to measure where the particle tracks are. So where do they fly through the detectors? And these larger fiber detectors have been made in the detector lab at GSI. So here's a view at that. And you see the colleagues working on the fibers and mounting that on the metal frame that we have. And these fiber detectors were produced such that they were put on a winding machine. And so you have these metal plates already covered in this black foil. And then you just wind the machine overnight, and you follow with a scintillation fiber that is on a roll, and you just wind it. And when you come back in the morning, you have a ready to go scintillation fiber area that you can use. And these fibers that we had here, then also covered again, of course, in this black foil, they were a bit larger. So here we had 500 microns thick fibers. And then they look similar like the small ones. So the idea that we had for them, the mechanics and the readout was similar. And here you can see them in their final shape when we had to move them into the vacuum chamber. So they had to go in there because we had to have them under vacuum. And the result of it, where the setup in this chamber is, you can see here. So we had 4 of these larger fiber detectors, which were mounted on drives that we could adjust them later. And on the very left, standing behind these 4 fiber detectors, you see the time of flight wall. And this is a view from the front, so actually sitting inside the magnet. This is how it looks like. So you might have an idea that we have the slits in between, while this is not the final position that we were using for the experiment. So this was already a bit later when we were doing calibrations and measurements after the experiment. And this is the TOF wall, so the time of flight wall at the end that we had used. So it's about 1.5 meters wide, to give you an idea of that size here in the picture. And it has these scintillator pedals now. They are 0.5 centimeter thick and 1 meter long. So the height in this picture is about 1 meter. And on the top and the bottom, they are read out with photomultipliers. And usually, well, this TOF wall is filled with scintillator pedals. And for our experiment, we took out the central ones to allow the high intensity beam to pass and not to hit our scintillators here. And this detector then, well, it's the time of flight wall, though in our experiment, this time of flight, yeah, we're using it, but not as a typical setup for R3B, where you would have a start detector at the front. So all the ions coming into the cave would go through the start detector. You have a start time and you get a time information from this time of flight wall, well, as it says, and then you get a flight time of the particles. But this, as we do not have a start detector, this is not what we're doing. But this detector can give us very nice information about the charge of the ions passing from the energy that they lose inside these rather thick, compared to the fibers at least, scintillators that we have there. And in the end, we have this C-trap, that you can see here, looking into this fragment arm from the vacuum chamber. And the idea is to use a secondary electron transmission, and this detector monitors that. So this is basically it's a very simple detector made out of 3 foils that are mounted. So you have 2 aluminum foils, which are very thin, and in the center you have a titanium foil. The aluminum foils you put on a voltage, and if the beam passes, then you may hit you may hit electrons out of that titanium foil, and well, they're attracted by the voltage you have in the aluminum foils, and that then you can measure the missing charge on the center foil. And by that, you get an idea, or you get information that is proportional to the amount of ions that have passed. So that you can get out of that. Okay, so that is the schematics of our setup, and I just wanted to give you an idea of what it actually looked like, what we have been using. And then we had a first beam time in April 2009. So the experiment ran for a short time, unfortunately, only. And well, but we were running after a long setup time, this experiment, and had the first, well, we have first data on tape for that. And of course, as you know, this is, well, if you're done with the experiment and you're at least a bit happy of what has happened, then you party a bit after that with everyone that has put so much work in it over the years. And now, of course, we're looking at data since the experiment, and I wanted to show you what the TOF-D can do actually for us, so the time of flight wall. On the left again, just to remind you how it looks like. And so you have then the pedal numbering as it is marked here, the scintillation pedals from right to left, because we have a right-handed coordinate system in our cave. In the plot, then you see the data that we get. So you have the pedal numbers in the bottom on the x-axis, and you have the charge that we get, the charge information from the top wall. And so for each pedal, you see that you can get a nice pattern that starts at charge number 2 and goes up to charge number 8. So this is what we have. We're shooting in a primary beam of oxygen 16 with the charge 8. That's what we see. And you can also see that although we had this a few centimeter wide slit in the top wall, we were still hitting the top wall and the pads with oxygen ions, but okay. And if you go a bit away from the slit, then you see nicely that the number of oxygen ions on it decreases, and that you see nicely actually also the charges that we're looking for, which are of course 2 for helium and 6 for carbon. And to give you another idea of that data, this is another plot. So this plot, it requires that we have 2 particles hitting the top wall. So this is what we were looking for. So we're looking for helium and carbon in the exit channel of the reaction. And what is plotted here is on the x-axis the charge number of the first particle. And then the charge number of the second particle on the y-axis. And because the first particle here is always marked as the larger charge number. You can see this shape that the plot has here. And well, here you can see all the charges that we have, and you see that we're actually nicely able to separate them. So then later for the further analysis that we will do. And then moving on, so we have the charge information, that is good. So we need to identify helium and carbon in the exit channel, what we can do with this, the charge information we get from the time of flight wall. And we follow the tracks of these particles with our fiber detectors. So, well, you have these 500, or for the larger detectors, 1,000 fibers, scintillation fibers next to each other. And where the particle passes through, you have a light signal that is then converted to an electrical signal in a photomultiplier. So we have information where the track, or the track is, so where which track did the fragment actually fly through our setup. And this is also what we need, so the track of that. So what is the idea then of the further analysis that we're currently doing? So to remind you, we have this Coulomb dissociation. And look at the upper part, again, at this very schematic view of the Coulomb dissociation. The oxygen ion is coming in and may be excited in the Coulomb field of the lead nucleus. So this is what we have on the one side. Then in the outgoing, you have helium and carbon. Okay. And, well, we use this information that we have, because in this moment, the one next to each other, so the excited oxygen ion on the one side and helium and carbon on the other side, there has to be energy and momentum conservation. And that is what we use for the further analysis. So what we want is to know what was the excitation energy of this oxygen ion. And we get that because we use conservation of energy and momentum. Okay, and here's the thing. We somehow now need the momenta of carbon and helium. And this is what we do by tracking the fragments. So you have an incoming track straight onto the target. And then the tracks go through the magnetic field and are deflected, of course, because they are charged. And they are deflected according to the magnetic field B and the radius of the trajectory in the magnetic field R. That is equal to the momentum over the charge. And this is what we use now here. Okay, and so to give you an idea how that it actually works nicely, here's some data where particles were tracked from simulated Coulomb breakup events. So this is where we start understanding our tracking algorithm, setting up the tracker. And so events were started with an excitation of 1 MeV above the threshold. And this is what a tracker gives back. So now we have the excited oxygen. We have a reaction threshold, which is something like 7 MeV, and on top of that 1 MeV more. And looking now in the after tracking at the sum of kinetic energies in the center of mass, then of the fragments. And you see that we nicely get an answer back that is around 1 MeV. So this works nicely for the simulated data, and we're now looking at the experimental data, actually. Okay. And now the next step then we have, well, we have done Coulomb dissociation, and if we have a cross-section as a function of the excitation energy that we wanted to just got from the information I showed you. But this is Coulomb dissociation cross-section. And now we need to take the next step and go to the actual gamma alpha cross-section, which is then the inverse reaction to carbon 12 plus helium goes to oxygen. And for that, we have to put in the theory of the virtual photons. So you can look at that in that the excitation in the Coulomb field of the lead nuclei is something like a virtual photon that puts that excites the oxygen with a certain amount of energy. And theory tells us then how many photons do we have as a function of energy. So that is what we know. And here is plotted exactly that, the number of virtual photons as a function of the energy for several things. Let me show you. So in black is the E2 component with a beam energy of 300 MeV per nucleon. And the kind of dashed dotted bluish line is E1 for the same energy. And then we were also looking for, we're just currently looking at whether it's a good idea to use 500 MeV per nucleon as a beam energy or 300 MeV per nucleon. And that's why this is plotted here. So this information we take, we know how many virtual photons are there as a function of energy. And that information together with the Coulomb dissociation cross-section as a function of energy, we can use to get an actual gamma alpha cross-section out of it. And this is what we'll do very soon now. Okay, and then we have the gamma alpha, so oxygen 16 gamma alpha cross-section, and from there we use the theory of detailed balance to get the actual cross-section that we want to have. Okay. So this was a rough overview of what we've done in the lab, and now also a quick view at the analysis that is going on right now. Many developments have been made over the last year and more. So we have the analysis running now, the tracking is running, and we're moving forward in big steps towards the cross-section that we finally want to have. Yeah. And going back, well, everything that I've showed you, you cannot do alone. You have to have a lot of people. You have to have people building detectors, setting them up. Then you have to do the beam time and cover days where you run 24 hours. And then you sit there and have lots of data that you have to analyze in a very intelligent way to find your very few events of Coulomb dissociation that we're interested in. Okay. So that was the idea. I hope I gave you an idea of what we're doing, and I'm happy to answer all your questions.
Yes, thank you for the great talk. We'll now take questions if anyone wants to jump in, or you can raise your hand or type the question in the chat, and we'll get through all of them.
I will stop that for a moment so that I can actually see you.
All right, I don't see any questions right now, so I guess I'll ask the first one. I've never heard of this sort of technique before to measure astrophysical rates. Has this been applied to other scenarios other than this sort of helium burning process? Or is this the first?
Yeah, so
okay.
We have been, our R3B and the before that land has been doing Coulomb dissociation. We're the first one to actually do it for this gamma alpha, so for a fusion reaction. What has been done in a few experiments is, for example, gamma N reaction, so a neutron in the outgoing channel, or also a proton in the outgoing channel. And then it depends whether you're actually interested already in the gamma-induced reaction, gamma N, or if you also actually want to know something about neutron or proton-induced reactions. So that has been done. Yeah.
Okay, thanks. All right, we have a question in the chat from Rob Farmer. Thanks for the great talk. How low in energy do you think you can measure the C12 alpha rate down to?
Well, this answer has two parts. So we have had this first experiment in April 2019, where we unfortunately had a few accelerated problems and could not collect as much statistics as we need to go down to low energies. So we have on tape data for the resonance regions where the cross section is orders of magnitude higher. So that's what we have. And currently, we are aiming for a second experiment. So there's right next week, there's the deadline for submission of new proposals, and that's what we're doing right now. And we aim now finally really to go down to 1 MeV and get an uncertainty that is less than 10% for that. So that is what we're heading. at, and which means that with larger uncertainties, we might even go a bit lower.
All right, we have another question in the chat from Manuel Coder. What type of priority will GSI FAIR give to a stable beam?
That is a good question. Yes, it is a radioactive beam facility as such. We had a bit of this luck that we were scheduled because there were problems producing radioactive beams in 2019, but sometimes you just have to be lucky. And now there is, yes, the upcoming 2 years might look like that there's 1 year with radioactive beams where we will not run, and another year where for I3B, there are actually 2 experiments now proposed with stable beams, and they might exactly fit to another experiment that will run for something like 2 months that will block the radioactive beam part. So that might be the ideal situation for the facility, because of course you have to get out the nice thing. And yes, radioactive beams are a priority at GSI, but still, doing this oxygen experiment with this high rates has also become an interesting thing for GSI. So I'm rather positive that this might happen.
All right, another question. Thank you for the nice talk. Which are the main sources of uncertainties in this measurement?
Let me think not to mess it up with the gamma n I'm used to. For this experiment, we are in the lucky situation that we do not have the uncertainties other Coulomb dissociations experiments have, because they have to have some absolute, absolute cross-section then in the end. But what we can do with all the systematic uncertainties that is usually has Coulomb dissociation, which are at least 10%, maybe also 20%. What we have is the nice thing that we have good data for this reaction at higher energies. And our experiment covers the whole range, then up to several MeV. So in the end, we can scale it. So if the shape fits, and we have a very good statistics for the higher energies, we can pin that down very nicely. So that is why we're so positive to go below 10% at 1 MeV in the end. And what comes in are all these uncertainties, and what you have to do for this Coulomb dissociation then is, well, I've shown you this ideal world that you have an oxygen coming in, hitting lead, and then you have Coulomb dissociation. But of course, you do not only have Coulomb dissociation, but you have nuclear reactions. And so we also do a measurement with a much lighter target, in our case, beryllium. Where you have, say, it's only nuclear reactions, and then you have to scale it and you have to subtract it. And so usually all of that gives you more than 10% uncertainty for sure. But in our case, well, we are hoping to be lucky because of the data situation we already have.
All right, any more questions? We've got lots of time. A lot of thank yous in the chat. Another question. So at even lower energies, or even at lower energies, you can reach 10%.
So the experiment we're proposing now, as we're proposing it, we're aiming at, well, we're expecting maybe 6 to 8% at 1 MeV, if that works out like that. From the statistics. And so, I mean, the cross-section really drops. It's horrible then, of course, at the lower energies. So we will not get very good statistics, maybe say at 800 kV, but I guess I'm hoping we get something. Well, then with a higher uncertainty, of course, but yeah, let's see.
Okay, any final questions? All right, I'm not seeing any. So thank you all for joining us, and thank you for the great talk.
Thank you very much, and for the questions. And
the talk will be recorded and posted online if anyone wants to refer back to it later. And we will have another talk on June 19th. The speaker's still to be announced, but I hope you all can join us then as well. All right, thank you all for joining us.